welcome. I've decided to start a little video tutorial series. So I figured in this video I would go over windows and internals and or some windows and internals, not really focusing on that, but that will be involved. But for this video I'm going to be going over function hooking, or you could call it detouring. But in particular, this method I'll be going over is a trampoline hook or a tramp hook for 32-bit. But if you can do 64-bit, you can do 32-bit. It's quite similar. It's more or less the same thing, really. But so let's get started. So the concept is essentially when you call a function, let's call it function apple. Call function apple. It's gonna do apple things, right? But the idea of hooking this function is before it starts running the actual function body, you're gonna wanna sort of intercept this sort of flow and make it run to our function called hook. You can call it whatever you want. I'm calling it hook. And the job of hook is essentially it takes all the parameters that Apple takes, and you can essentially decide to change the behavior of Apple, modify the parameters. You can overwrite the behavior completely. Well, you can do whatever you want, more or less. You're intercepting the call flow. And that means you have the option to resume the call flow back to Apple so you can, well, do the Apple behavior. So this could be useful, for example, if Apple takes a parameter of how many apples, just for the sake of example. So if we have one apple and I'm feeling extra hungry and hook, then I can change the number of apples to 25, for example, and then resume the call flow with 25 apples rather than one. That's a pretty simple example. Another example where you might want to do hooking is if you have an interesting app, like this app, Paint, and you want to figure out every time it's accessing a file. So then instead of hooking the function Apple, you hook the function within the Windows API called create file and then A or whatever. You can just hook the file creation. So the function I've decided to hook for this video is MessageBoxA, because that's a nice function to hook if you want to see something change. So the idea is that we're going to hook this and change the text that it displays. Maybe track how many times it's been called, just simple stuff. Just to demonstrate the idea of hooking. And yeah, so there's a few key things that you need to understand for the theory behind hooking, and it's how does it work, what are you actually doing. Like, you want to call another function, but how? So the bytes here on the left, this is using IDE freeware, some disassembly software for reverse engineering and all that. So the bytes here directly translate into these instructions here. So this is quite literally the file that gets executed. This is exactly what's being run. This is the machine code or the binary code, whatever you want to call it. So these bytes here directly translate into this instruction here. So move register EDI into EDI. So essentially do nothing. And then push the base pointer to the stack, and then move the stack pointer to the base pointer, etc. So that's what these bytes translate to. So for the function hooking, we're going to need to take the first instruction, so the bytes here, and replace them for a jump instruction to our hook. So the bytes in particular that we need to change is this 8B, FF, 55, AE, and 8B and EC. So this jump instruction is a 5-byte sized instruction, and the way that works is so the byte for this is E9, And that essentially turns this first instruction into a jump instruction, which I can actually demonstrate. But I want to save this as a file because then I'll probably break quite a lot. What am I thinking? Patch. So if I change this to E9, we're expecting to see the 1, 2, 3, 4, 5, these instructions here to change into one jump. And it should be the same from the comparison onwards. So change this to E9. And there we go. I'm just going to redefine this function now because... Oh, wait, no. So this is the reason it's not picking up the rest of this function as sort of involved with this is because a jump will literally just jump. A jump doesn't really expect to be returned. So the bytes here, this E9, FF, 55, 8B, and EC, the way this works is it's a relative jump, meaning that it takes the address of the instruction, but in reality is the end of the instruction. So these 5 bytes are at this address right here. So 90, address ending in 90 is E9. Then you have 91, 92, 93, 94. And the jump will actually be executed at 95. So just right after this instruction. So this is where the calculation is sort of based from. So for example, if I take this address right here and I figure out what this is as a number, as a signed integer, because in order to be able to jump backwards, you can't have an unsigned relative offset because then you can only jump forwards. So this is a signed value, not an unsigned value, which is a useful detail to know. Might be able to compute this with a calculator. So the way you type this into the calculator, because it's little endian, meaning that the number on the most left is the smallest of values. But when we have a number like, for example, when we have this number here, this is the biggest value. This is how we humans read it. So you have the biggest on the left, smallest on the right. But in this case, it's the smallest on the left and the biggest on the right. So the way you would write that out is x86, 8B, 55, FF. And this is sort of separating all of the bytes, but in a backwards order. And, well, yeah, that's basically how that works. So the location of this jump is going to be this address, right after, so this address, plus this offset. So let's have that in here, because this console here doesn't support signed values, I don't think anyway. So EC 8B 55 FF. So this is minus a few million. So we grab that value, subtract it here, and we get exactly what this thinks the destination is. So everything agrees. Cool stuff. So the last step of this is, how do you resume the original call flow of MessageBoxA if you've overwritten the first 5 bytes into a jump instruction? So if this jumps to our hook and then we call MessageBoxA from our hook, all it's going to do is create an infinite loop of jumping to our hook. So how do we resume the call flow to execute the rest of the function essentially? So when you overwrite the first 5 bytes, you need to make sure that the bytes that you overwrite contain full instructions. So let's say, for example, if we ignore this instruction here and our function actually started here rather than there, just to demonstrate that, I'll just make it nicer to look at. So let's say our function starts at this address. So if we overwrite the first 5 bytes to a jump, we take 1, 2, 3, 4, 5. We see we have these trailing bytes here. So we can't just have some corrupted instruction to resume from. We need to include these bytes as well. So because the jump itself is only 5 bytes, we're not going to extend this into an even bigger jump instruction to cover the rest of them. We're going to nop these out, nop as in no operation, and it's essentially just going to turn into like an empty instruction. So the last thing that you need to understand is the gateway. How is it built and what actually is it? So the gateway is essentially the function you call to resume the original call flow. So if you want to call the original function while a hook is implemented, you call the gateway. So the gateway is built up of the first few bytes that you've overwritten. So in this case, it could be 8BFF55 8BEC, and this will translate into these instructions here. Or for the sake of example, let's say we ignore that first instruction just for the sake of example. And let's say our function just starts here. But in this case, it starts there. But for the sake of example, pretending this is an entirely separate function, let's say it starts here. So then instead of having these first 5 bytes in the gateway, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because the first 5 bytes are making up these few instructions here, but we can't have these trailing bytes, so these get included as well. So we have 55, 8B, EC, 833, D, 2C, 9C, EC, 6900, or whatever. So this is going into the heap. So we need to allocate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes. So how do you actually return the original call flow? So after placing these bytes into the heap, we need to write one more jump similar to how we've written one here, and we need to write the jump to continue from where we left off. So if this is all getting turned into a jump and these are getting turned into nops, we need to jump back here because we already have these instructions. These are rebuilt. We need to jump back here. So then we write another jump, so E9, and then the relative address to resume from. And this is essentially the entirety of the gateway. So for recap, the call flow goes from original function to the hook to the gateway to resume original function. So this is essentially the final call flow. And yeah, that's it. So now we're going to get into implementing this. So I've written up this sample code, and all this code does is takes your input and spits it back to you using the message box. So MessageBoxA is the function that we're hooking. So for the sake of going over everything I've explained and writing the implementation for this, I'm just going to write a step-by-step of what needs to happen. So first let's define the function templates first. So we have the Tramp hook function, which is going to return a void pointer because it's a pointer to the gateway. It's going to take the target function, it's going to take the pointer to the hook, and it's going to take a size. So the target function is the function we want to hook. The hook is our function that it's going to call, and the size is how many bytes do we need to overwrite. It's the size of the hook. For the sake of making it easier to understand, I'm going to write this helper function called jump. It's going to take the source, it's going to take the destination, and well, yeah, it just writes a jump from, it's going to write a jump at this address that lands here. So we're going to cast this to an unsigned char. And then the byte for a jump is your E9. And then we need to write an integer, not an unsigned integer, a signed integer, into jump +1, because jump is, well, this is the parameter. It's the 4 bytes after the E9. That's why it's a 5-byte instruction. And this is going to be the destination minus the source, but then the source +5, because it jumps from the end of the instruction. And that's it. So this is now a function that just writes a jump. So what we need to do is, in order, we allocate some heap executable. Let me just put that here. Allocate some executable heap with size plus 5, because size is the size of the hook. So 1, 2, 3, 4, 5, and then plus 5 for the actual jump instruction to return here. Then we need to copy original bytes to gateway. Then we need to not the original bytes, I guess. Then jump to gateway. Jump to gateway from original. Oh, no, jump to hook from original function. So you can only do this after you've copied the original bytes, because otherwise you've lost the original bytes. So that's why you need to implement the jump to the hook. Well, as like the fourth or third step. Then you need to jump to original function from gateway. And I think that's it really. That's just a few little intermediate steps that I'm missing, such as page protection, but that's basically everything. There's not much to it. So we need to check if the size is less than 5. If the size is less than 5, then that's not a big enough function for us to write a 5-byte jump into. Next, we need to allocate the gateway. So we're using virtual alloc to let the operating system allocate some heap for us. And then we're passing null to the address because we don't care where it gets allocated. Then we're passing size plus 5 for how much heap we want. Allocation type is going to be mem commit and mem reserve. And then page execute read write. So what this means is that it's essentially protecting it's allowing our allocated heap to be executable, and so that you can read and write into it. So now that we've got the gateway, let's just add a little safeguard there. Next, we need to change the page protection of the target function. Make sure we can overwrite the bytes in there. Make it execute read write, and then store the original protection. And then also restore the original here. So next we need to copy the original bytes. And then not the original bytes. So yes, that's the destination. So the target function 0x90 for this many bytes. 0x90 is a NOP. And then we just need to write 2 jumps. So write jump from the target function to our hook, and then 1 more jump from the gateway plus the size to the target function plus the size. And then we can cast these to unsigned chars, so we can do some simple arithmetic. And yeah, that should be it. So now what we need to do is return the gateway, and this should be our implemented Tramp hook. This should work. So when it comes to hooking functions, you need to be able to call the original function as well. So we create a little type def for this. So it's just going to copy the original function template, which is literally this. probably just come here and steal it. So it's going to be type def. No, you know what, I'll just do it the proper way. That's messy. So it's a function that returns an integer, and then it's going to use the standard call convention because this is how the Win API does it. You can also find the call convention here. And then we're going to mark it with a T, meaning template, T, MessageBoxA. Then it's going to take the parameters. I just can't be bothered to define them. And then we're going to define a variable that stores this original function. Let's just call it gateway. And that's it. So now we need to define our hook. And then at the end of this, we can return the original function. So we have the original message box behavior. If we don't do this, then calling MessageBoxA won't create a pop-up. So yeah. What's left? We can do a static int times called plus plus. MessageBoxA was called times. And in here, we implement this actual hook. Let's add an extra little guard so we don't hook the function twice, otherwise that'll create a big mess. And not a MessageBoxA gateway. Check this as a null pointer. This is quite a lengthy name. I'm just going to call it this. And not a MessageBoxA. And now o MessageBoxA equals, let's cast this to a T MessageBoxA, and then Tramp hook, the target function. So we need to get the MessageBoxA function. So we're just going to do get proc address, get module handle, get which DLL this function belongs to, and let's go to MessageBoxA. The hook is going to be HK MessageBoxA, and the size is going to be 5. And if we do this, now if we call the function and run the program again, we have the original behavior. We type hook me, well, we get the text, and then we see our code is getting called along with MessageBoxA as intended. You can do similar things and just overwrite some parameters if you want to change how it works. And just like that, you've written a Tramp hook. Pretty simple. To demonstrate this on a lower level, I'm going to attach to this program using Cheat Engine and walk you through exactly what's happening to the code, the hooking process. Think about this. Okay, so let's go to user2.messageBoxA. Okay, so gonna add a breakpoint here. What? Maybe I need to rerun this. That's interesting. Oh, okay, I understand. It's because I'm compiling it in release. So if I reattach this, oh, didn't even know you could do that. MessageBoxA. see the original behavior. Let me type in hook me, and we can start walking through this. So it's just allocated some heap at this address, changing the function, the page protection for this function. Then we need to copy the original bytes to the gateway. So we can see that the original bytes is 8BFF558BEC. So we can watch the gateway get constructed. So step over this instruction, and we see we have the original 5 bytes here. And then it's nopping the original function. So we're going to see all of this essentially vanish. And it's just been replaced for nops. Next, it's writing a jump to our hook right here. So let's step over that one. And now we see it's a jump. Lovely stuff. So this is the function it's jumping to, which is just jumping to another jump. And voila, this is our hook. So we can watch the final jump getting written in by at the gateway. So voila, so we have the original bytes. So this is the gateway. So this is how you call the original function. So it's got the original instructions, and then it's going to call the rest of the original instructions. So it's just got the top part and then the rest of it. And yeah, I mean, that's it really. And just like that, you've got a pretty simple hook. So the last thing that you need to keep in mind is restoring the hook. And it's pretty simple. So let's call it restore Tramp hook, target function, hook, size. And all this is going to do is change the, it's essentially just going to copy the original bytes from the gateway into the target function. So for this, you need to restore the, to change the page protection. So target function for this many bytes, page execute read write, and mem copy to the target function from the gateway, and for this many bytes, and then virtual free the gateway size mem free, or mem release maybe both, don't remember. Whatever, I'll just do mem free. Let's actually just consult the documentation and go for what looks more appropriate. Let's do mem release and see what happens. What's the complaint? Okay, whatever. Let's see what happens from there. And then the return value is successful if it's non-zero. Let's just test it like that. And then virtual protect, target function, size, order protection. So simple as that for restoring a hook. Now that's basically all that's left. So let's just add an extra little comparison. Target function. Let's just copy these parameters and then change that hook into MessageBoxA. So let's test this. Or let's make this null pointer afterwards as well. Then hook me. Oh shit. So it's at a breakpoint because we left that behind. And then we see it's calling our hook. Let's call restore. And it's restored the function. So, lovely jubbly. And it does appear that we used the correct virtual free. So yeah, that's all looking good. And that's how you implement a Tramp hook. I hope you found this video useful, and yeah, I'd appreciate some feedback.